Hello and welcome to my presentation. I'm Jinyao Zhang from Xidian University. In this presentation, I introduce a hardware-software co-design framework for acceleration on systolic array. To accelerate multiply-accumulate operations in deep neural networks, systolic arrays are introduced as an attractive platform due to their high degree of concurrent computation and high data reuse rate. Google's TPU is the most well-known accelerator based on systolic arrays. Here's an example to show the process of matrix multiplication with the weight stationary systolic array. At the beginning, weights are preloaded into processing elements, and then the inputs are streamed into processing elements in a particular order. In step 1, input 1 is pushed into the array and multiplied with weight 2. In step 2, input 1 is transmitted to the downstream processing element, and product 2 is transferred to the right processing element for addition. In step 3, the final result 17 is stored in the appropriate position of output buffer. Each processing element performs similar functions, and the whole systolic array can complete the multiply-accumulate operations. Weight pruning is considered as an effective method to compress neural networks for acceleration. However, sparse matrix multiplication cannot be computed efficiently in systolic array, since the array is not good at exploiting irregular parallelism. The left figure shows a weight matrix after the unstructured pruning. The blockwise method covers the sparse weight matrix with a fixed size block, so that many unimportant weights remain in these blocks. In addition, weights outside of the blocks are discarded directly. Therefore, it cannot provide a high compression ratio while maintaining the accuracy of neural networks. The column combining method squeezes several columns into one column. However, many non-zero weights are discarded, potentially leading to a degradation of inference accuracy. In addition, this method incurs extra hardware costs for multiplexing inputs in the systolic array, since it breaks the vertical data dependence of the systolic array. To utilize the systolic arrays efficiently while guaranteeing a high compression ratio and high inference accuracy, we propose a hardware-software co-design framework considering both the latency and hardware cost of systolic arrays for convolutional neural networks. By row swapping, block selection, systolic array multiplexing, and genetic searching for multiplexer assignment, a flexible systolic array structure can be developed with accordingly pruned convolutional neural network models. Unstructured pruning is chosen to prune the weight matrix first due to its high compression ratio without accuracy loss. After unstructured pruning, we propose a row swapping method to store the sparse weight matrix densely. This method not only preserves the compression ratio of the weight matrix, but also requires smaller memory storage, since only rows with non-zero weights should be indexed when each column has weights, and a small number of columns should also be indexed when some columns are empty. After the proposed row swapping, all the remaining weights are pushed into the bottom of the weight matrix, forming a dense cluster to make block selection feasible. The weight matrix after row swapping forms a dense cluster with an irregular shape. Therefore, it is difficult to find a single block to cover this irregular weight cluster seamlessly for the efficient implementation known as systolic array. To solve this problem, we propose to use different sizes of blocks to cover the reorganized weight matrix seamlessly. The proposed method provides a finer granularity of coverage for the irregular weight matrix, so that no weights are discarded and there is no inference accuracy degradation. After block selection, the optimal block combination can be generated for a given convolutional neural network to reduce its inference latency and hardware cost. When weight blocks with various sizes are mapped on systolic arrays to implement the matrix multiplication, the corresponding inputs for the weight blocks are not matched. To support the concurrent computations of various blocks with the corresponding inputs on systolic arrays, multiplexers are inserted into the arrays. To support the row swapping, a controller and selection modules are required to schedule the multiplication results. The computation of modified systolic array is shown in this slide. Assume that we have weight 1, 2, 3, 4, whose row indices are 2, 3, 3, 3, and related inputs are 5, 6, 7, 8. First, controller decode row indices of weights. Second, array loads weights. Then, array loads inputs. Since multiplexers are enabled, these 4 inputs can be loaded at the same time. And then, each processing element multiply weights and inputs and transmit products to selection modules afterwards. Simultaneously, controller sends signals to selection module. Selection modules then handle received products. If weights are in the different row of the weight matrix, selection module stores products respectively, in this case 12 and 5. If weights are in the same row of the weight matrix, selection module adds products and store the addition results, in this case 32 and 21. To support different convolutional neural network models on systolic arrays, genetic algorithm is implemented to search the locations of multiplexers to achieve a flexible systolic array structure. According to the locations of multiplexers, a flexible systolic array structure can be proposed with low latency and low hardware cost for various convolutional neural networks. After figuring out the computation of the modified systolic array, we can evaluate each possible block set, considering both latency and hardware cost. We select the block size that represents the best trade-off between latency and hardware cost minimization. Table 1 demonstrates the comparisons between the unstructured pruning and the proposed framework with different convolutional neural networks. The inference accuracies of all convolutional neural networks with the proposed framework are higher than those after unstructured pruning, as shown in the third column of this table. The reason is that the proposed method recovers some of the originally pruned weights during the block selection to cover the weight matrix. Though more weights are preserved to fulfill the blocks, thanks to the systolic array multiplexing, the total latency is reduced significantly, as shown in the 7th column. The number of multiplexers to achieve systolic array multiplexing and the ratio between the number of multiplexers and the total number of processing elements are shown in the last 2 columns. It is clear that the cost of the inserted multiplexers is trivial for the total hardware cost. Left bottom figure shows the evaluation results of all block combinations for each convolutional neural network in the 64 × 64 systolic array. Right bottom figure shows the flexible systolic array structure after genetic searching. The initial systolic array is determined by optimal block sets of each supported convolutional neural network. 47.81% of multiplexers can be removed without significantly increasing the latency. In conclusion, a hardware-software co-design framework is proposed to exploit systolic arrays for the computations of various convolutional neural networks efficiently. And second, by row swapping, block selection, systolic array multiplexing, and genetic searching for multiplexer assignment, a flexible systolic array structure is developed with accordingly pruned convolutional neural network models. The experimental results show that the latency can be reduced significantly with low hardware cost and high inference accuracy. Thanks for your listening.